Okay, I'm very sorry. Extremely sorry for the audience for the delay, about 9 minutes. Now, what exactly happened is I, for the lecture, today's lecture, I created a PDF which somehow overwritten by the previous days. So I have both the previous days copies, 2 copies. So I quickly made the second today's copies again. Okay, so due to that it was delayed. Fine. Okay, so I think we can start the session. I hope you can see my screen. Yes, you can see my screen.
Yes,
Right.
yes.
The voice is clear. You want me to use some?
Yes, yes. Your voice is clear, sir. No issue.
Voice is clear. Great. Okay. So what you can see here, we started with yesterday. What is quantum sensing? Okay, right. Just a minute. Okay, let me go to scrolling. Yeah. All right. So before going into quantum sensing, we need to know few things. Like it's a part of quantum physics. Probably it might have been introduced to you already, but I want a revision so that there will be connectivity with what I want to teach or convey yesterday. So for that, I had brought in how qubits evolve in time. So we used a time-dependent Schrodinger equation. Okay, so what you see here in the bracket, so this part, and using that we got to see we could get some evolution operator or transformation matrix which tells which connects the quantum state from older time to newer time. So interestingly, that quantum operator happened to be a unitary operator. We saw that, how to prove it. Okay, and now that operator happened to contain the system information. That's a Hamiltonian information. It's called a system energy matrix, H. Okay, right? So if I happen to know the energy matrix of a system, I can construct a unitary operator out of it. And having the unitary operator, I can exactly know how the system would evolve in time. Okay, right? So that is the very information I would be needing. Along the way, I have used operator form for the energy, okay, which is IH cross dou by dou t. See, A is like a number usually for us, so which becomes an operator, like some can think a derivative, a time derivative in the quantum physics or quantum mechanics. Why it becomes? We just saw a derivation. Similarly, the momentum operator or even the position operator also becomes like a operator. So momentum operator takes a derivative with the space, and position operator just a multiplication by some number. Okay, so there is not much in the position operator multiplication or operation. Okay, we will see that today. Now, having that background in quantum physics, we just straight away went into quantum sensing. What is it? What it actually needs, devices wise. It's a superconducting quantum interference devices. It's actually SQUID. So there is a small typo here. I just wrote a semiconductor. It's not a semiconductor. It's a superconductor. Okay. Now, not only that, there is something called spin qubits and trapped ions, and flux qubits could be used to do the sensing. And spin qubits and trapped ions, you all know. And flux qubits, something very different from the other two, which is a kind of a circuit we artificially make, right? So superconducting Josephson junction based superconducting loops. So they interestingly forms a qubit in terms of basis states realized out of current direction. That is what I showed here in the corner figure. Okay. So we could exploit the weakness of the quantum system or fragility of the quantum systems to the external surrounding. In that way, how much they vary with the surrounding effect, we could define or describe what is the surrounding actually made up of. Okay. I'm sorry. So this idea of using this kind of a fragility was not only now being explored, it is started in 1931 itself by a scientist by name Wellston. Okay, and even we can use quantum entanglement to enhance the accuracy or sensitivity of this sensing. So that is a new trend these days. Okay. So what is quantum sensing describes in a nutshell? Also we have seen. Okay. And the question is there every quantum system could be used for sensing? Of course, no. There are particular systems only which allows for sensing, and there is some set of rules or criteria need to be followed, which is actually inferred from the De criteria. Okay, and so the types of quantum sensors could be classified based on how they respond to the external means. Okay, so one is charge systems which responds to electric field. The one is spin-based system which responds to the magnetic field. Okay, so one has to balance sensitivity. In a way, the system should be sensitive to the external field, but not much sensitive to the noise. Okay, that is a very tricky thing to have, because whenever a system I say it's sensitive, it is sensitive to everything. But one has to balance in such a way we could have a better sensor which is less prone to the noise. Okay, fine. Now there is a methodology involved, initializing the quantum system, interacting the quantum system with the environment. And I want to study the environment, that's why I made it to interact. And then how the system evolves, I analyze and I'll find out what is the system being exposed to. Okay. Now we just discussed the mathematical description. I'm very sorry. This is actually we need to go through, because if I was asked to give the basics of quantum sensing to undergraduate level student or any even master student, I could skip some part of mathematics. Okay, but the thing here is, if you see, the mathematics is very much needed, and as a faculties, you all participants must know what is the basic mathematics, right? Then only once you understand, then only you can convey or make the student to understand. Okay, so there is no other go. So that's why I am just requesting you people to have a patience and go through my notes, right? It's actually straightforward, it consists of everything. Now coming back to the content. Here you see the mathematical description of a quantum sensor. I would start with the system itself. It's consisting of some energies that I will put in the form of some energy matrix. It's called energy Hamiltonian. So the system would have its own Hamiltonian. For the time being, you can say the system is not exposed to an environment, so it will have H0 as a Hamiltonian. If it is exposed to the environment, in that case, I will have an interaction Hamiltonian. Here I am calling it HV. And I want to control the system, the sensor, so that it controllably interacts with the environment, not uncontrollably. Right? So yesterday somebody was asking, is there a situation where system goes and entangles with the environment? Okay, so that is a good thought. Let's say I don't want, in that case I would use this H control to only to interact in such a way. I just need the information of the environment, not too much fiddling with that. So that could be done using H control. Okay, so specific I gave specifically what is H0 would look like here, if you see. And when it comes to the system Hamiltonian, interaction Hamiltonian, let's say a signal or surrounding environment which is represented as a signal, that would have two contributions coming from a parallel component and vertical component. Okay, so the parallel component is something which in parallel with the alignment of the qubit. The perpendicular component is the one which is perpendicular to the qubit. So qubit could be arranged, let's say spin qubit, if you say, it could be a up spin or a down spin. So the parallel component would be in vertical plane, and perpendicular component of Hamiltonian would be in the horizontal plane. It would be arranged. Okay, so that I have given you here, and specifically what the parallel component would look like, and perpendicular component would look like I have given. And there is small typo here. If you see the fourth term in a matrix, HV matrix, there is a minus sign missing. Please note down that. So the small typo there. Okay, So I'll just tell the small any corrections during the class. Now, if you just see the parallel component effect, would be stretching the quantum state or quantum energy separation between the qubit states. Okay, that is a parallel component effect, and perpendicular component would enforce the unnecessary transitions from some excited state to the ground state. It's like a relaxation. Okay, so that I don't want. So I want in a limited way, so that I would notice how much is the strength of the perpendicular component. Okay, so that is the HV for you. And when it comes to H control, right? So one can use the basic gates like Hadamard gate, Pauli gates, and rotation gates are controlled, even control not gates if I am using more than one sensor which are together working in tandem. So in that way, I would be needing control phase gates also. Fine. Now, here I have not given explicitly what is the H control part. Like I said, I would be needing a Hadamard gate, so I can easily calculate the corresponding H control for that. Okay, depending on the gates, I can find out what is the H control. Okay, now coming back to the sensing protocols. So the sensing protocol I have given in steps here. I would prepare the system in very fundamental zero state, a 0-bit state, or a classical bit state, which is quantum mechanically is a 0 kit. Then I put that into superposition state by using some unitary operator UA. Okay, so that superposition state I have put under exposure to the external field or external Hamiltonian. Okay, so because of that, I would see there is a change in the quantum state, which could be combination of new state and the old state. Okay, or even completely new state. That is also possible. Now, if you carefully see, the state which I evolved would not be in a measured form, because sometimes I would say, because I don't know in what basis it is coming out. So I want to, without losing the information, I can just convert the basis into observable basis states. The observable basis states are 0 kit and 1 kit. How do I do it is just to take the evolved state, okay, the evolved state alpha, I'll take alpha kit, and then take a projection of this alpha kit onto the observable 0 kit and 1 kit. Okay, so if I do it, I would exactly know what is the chance of the evolved state to falling into 0 kit, and what is the evolved state chance of falling into 1 kit I would be knowing. From that, I can make out what is the external signals impact on the quantum system or a quantum sensor. Since I can't just make out the information of the signal with one experiment, I would be needing to do the same experiment several times. So there I will get the set of probabilities. Okay, from the set of probabilities PK, I would easily make out what is the signal is actually made of. So the same thing, it is given in the form of algorithm. So it's like in a summary way, right? Whenever I find there is the quantum output or the probability output is not sufficient, I can go back and read the same thing. That is what I have shown at the very end. Okay, it's like a feedback loop. Now, this is about the quantum sensing, the basic part, how it is mathematically described, how it is algorithm way it is described. Yeah, I have discussed now. Okay, now if I have to understand how the algorithm works, I have to get in to actual real world examples. Okay, if somebody has any questions, please let me know now. Okay, there are 380 plus people are there. Okay, right. So yeah, I have shared the research paper already with regards to yesterday's lecture notes. Today it is there in the sharing platform Canva, which is I also joined yesterday. So under the quantum sensing lectures, it is there. Okay, fine. Now coming back to the examples, like I said, we will discuss the examples here. Okay. So let's say I want to find out a effect of the parallel signal V parallel. What you see on the title. Okay, V parallel is there, right? Now This is actually called a Ramsey interferometry. Okay, so it's called a Ramsey interferometry. Basically, it's something to do with some two fields are there, they're interfering, and something interferometry is there. So let's keep that aside. As per our algorithm, let's say I want to detect or find out what is this V parallel is made up of, the signal parallel component is made up of. First, what I do, I take a quantum state which I prepared in a zero ket state. Okay, that's the first step, what you can see here, right? So the first step is this one. Okay, right? So is there a marker I can choose somewhere here? Okay, yeah. Right? Fine. So now I prepare the system with a quantum state. Okay, right? And now, after preparing, I want to put that into superposition state. So for that, what I do, I take that 0, right, and put it into put that into a superposition state by acting some pi by 2 tuples. Basically, it's just a harmonic gate. What you see here is okay, right? Fine. This is harmonic gate. Oh, it's not underlying. Yeah. Fine. Now, next. After that, I want to expose that to the system environment. So the environment is defined by some Hamiltonian H. Remember, the H is represented as H naught for the system itself. And if I add the environment information also, it becomes a overall H. With some control parameter, it becomes overall or total Hamiltonian. Let's say as of now, system is not exposed, it is having only H naught. So in that way, you can easily find what is the unitary operator. Okay, so the unitary operator is found. Fine. So I have H naught here, right? I can just remodel H naught in terms of energy separation. So same thing, E naught, E1 as a diagonal is same as in the last term being the separation of E1 to E naught. Okay, so that is actually allowed. Now, having the H, I can easily find out U. U acting on the quantum state, you see here, would lead me to the new state, which is represented in terms of 1 over square root of 2 column vector 1 by, okay, 1 by 1 into exponential minus I omega t. That is what you see. So basically, that is a time dependent quantum state. So this is what you see in the bracket. Okay, right? Fine. Okay, this is done. Now let's go to the next state, next stage. Okay, the next stage is, let's say, evolved state, I want to put it back to the readable state. Okay, that's what I have to do. So for that, okay, before that, let's say now I will bring in overall Hamiltonian H. Okay, and that, oh, sorry. Okay, I'll have a Hadamard gate by pi by 2 pulse. I will act here, converting the evolved state into measured state by using another pi by 2 pulse. Remember, the pi by 2 H matrix acting on psi has an impact. If there is any zeros in it, zeros would be converted to superposition state. If there is ones in it, that would be converted to superposition. In that way, it ensures that, okay, the overall state would consisting of observable basis elements. Okay, so observable basis elements here you see there is a 0 ket, there is a 1 ket in the alpha. Okay, fine. Now I just find the probability of, if I make an observation on this system, what is the chances of getting 0 ket? What is the chance of getting 1 ket? That can I easily make out. How? I just take The inner product of alpha with a 0, that would give me the probability amplitude of this one. Okay. And if I want to know what is the probability of getting 1, I'll just take a probability of amplitude of this one. Okay. Right. So this one. Fine. Now, so let's say I just find what is the chance of getting probability 0, this one, and I just subtract from 1, I would get probability of 1. So if you just carefully substitute 1 minus 0 and alpha inner product whole square, that is the probability of getting 1, right? If you just carefully follow through, it is already done. So just excuse me for a small calculation error. So I just write that off. Okay. Now, if you just find out the probability of getting 1 is actually sinusoidal function. Okay. So like a formula which I used, exponential I theta formula, which is there in the next page. Okay. Right. So using that, you can see the probability of finding 1 in time is actually sinusoidal function. If you plot it, it would look like this. Okay. This is what you have. Right. It looks like this. Now, what you see here is a probability is being oscillated. So can I make any information about the quantum signal, which is quantum sensor is actually detecting? So how to do that? Let's go to the next slide. Okay. Okay. Okay, let me say here itself. So what I'll do, I'll just find the slope, right? So the slope means rate of change of P, right? With respect to time, I would get. Okay. So from the rate of change of P with respect to time, the slope, from that I can make out what is the effect of V, right? Which we will see in the next example. So both this, whatever example I was discussing here, that example and the next example, both are same. Okay. So at a time we'll discuss both of them. Okay. Now, let's say I want to find out the perpendicular component effect of interaction or a signal on the sensor. Okay, this time again, let's say I'll start with the I'll start with the 0 ket and then put that into superposition. Okay, let's say there is no internal Hamiltonian, the system remains in 0, right? Okay, till some external intervention is taking place. Okay, now let's say I have an interaction Hamiltonian, which is a perpendicular component is this way, where there is a Pauli matrix is involved, right? Fine. So V perpendicular multiplied by Pauli x would be simply sigma x, right? Okay. Now under this H, in inclusion of this H into the overall Hamiltonian, I could easily find what is the effect of this on the system which I started in the first place. Now the question is, since H0 is 0, there is no V parallel, let's say, the only contribution for the Hamiltonian is coming from this. So in that case, I can just find the unitary operator using this HV perpendicular. Okay, so I got the unitary operator. If that unitary operator acting on the quantum state 0, which is I started, I would be getting some state which I can easily calculate by using Pauli x. Okay, so Pauli x acting onto 0 ket, I know that is a x ket acting 0, but it is the exponential of Pauli x with the omega 1t multiplied. Okay, so I have gone from the line, this line to this line. How did I go? That I have in the next slide. So next few slides, we can just wait until that. So for the time being, let's choose this. This is how I got this. Okay, let's say I got this final state, which would look like this, more or less very close to the previous situation. Okay, since it is already in 0 and 0, So this is already in 0 and 1 ket basis. It is in observable basis. I no need to do any conversion here. Okay. So I'll just straight away take the inner product of this quantum state with the 0 ket. I'll get what is the chances of getting 0 when I make a measurement on this. Now, if I substitute, if I subtract that probability from 1, I would get what is the chances of getting 1 when I make a measurement. Okay. So if you see here, this is also happened to be a sinusoidal function. Okay. Just like the previous case, this is a sinusoidal function. Now there is a difference between the previous case to here is probably the omega, the angular frequency. You see, the omega in this particular case is actually dictated by the energy of Hamiltonian, energy separation, H omega naught, energy separation of the qubit itself. So that is the frequency of this particular probability in the Ramsey measurement. In the case of Rabi measurement, the V perpendicular measurement case, okay. So what I see is the sign function is function of omega 1. What is omega 1 here? Omega 1 is the component which comes from the V perpendicular. Okay, you remember that. Now, so the question is now, how did I get from exponential of a matrix to some operator form? How did I get from here to from here to here? How did I get? So that I have here in the next slide. Okay. So if you want, okay, just a minute. Okay. Shall we need? Do we need to? Okay. Do we need to discuss? Yeah, I think I have somewhere. So L. Okay, just a minute. Yeah, I have it here, all the way here. How sensing small signals is done. Okay, right. So quickly, we should find out how did exponential of some sigma x, okay, some sigma x becomes some operator form which we can take it. Okay. Now, so in general, exponential of some Hamiltonian matrix could be written like this. Okay, right? What you see here, right? Okay. Now, what is the exponential of something? Exponential of something, if it is a complex number, exponential of I theta, I can write it as cos theta minus I sin theta. Okay. But the thing is, I have a matrix here, so which I can show that as exponential of my minus I matrix is equal to cos some factor into identity matrix, I into sine of some factor into some sigma, whatever sigma h I was using here, where h is a, okay, right, where h is a energy vector. Okay, fine. So now, how did I do that? In this particular situation, what is my h vector? Don't confuse with the Planck's constant. This is a h vector, energy vector. For h vector, I have one I. Okay, which has only x component, and sigma into h would be just a sigma x. In that particular case, if I substitute in the above equation, I will get cos minus I omega 1t into sigma x as like this. Okay, right? So once I get that, I can easily substitute what is cos omega 1t into identity, what is sine I omega t into sigma x. Okay, sigma is just a x function, x matrix. So if I substitute, I'll get overall exponential matrix, right? Okay, if that exponential matrix acting on 0 gives me this part, right? So you just do some simple, okay. If I just use simple trigonometric conversions, I can show exactly what is the evaluated overall function, right? Right. That is what I have used here. Okay. Fine. So let me go to the. Okay. So what is the exponential of a matrix? Correct. Hermitian matrix. Since our Hamiltonians are all exponential matrices, so I have here explicitly given for the Hamiltonian based matrices. How do I get unitary matrices? Okay. So usually exponential function means what? So what I'm trying to prove here is just a minute. What I'm trying to prove is how did I come up with this exponential of some H matrix would give me this. Okay, that is discussed in this slide. Now, simply exponential of x means what? It's a summation of x of n, x to the power of n divided by n factorial. Okay. Now, for me, unitary operator would be exponential of minus I sigma into a. Okay, where a is just an energy vector. For example, in the case of electromagnetic fields, there is an energy vector. So that is what a vector is. So a vector is written in terms of h bar divided by h cut into t, where h cut is the Planck's constant and h bar is the another scaled version of energy. Okay, right? So now just simply find out what is sigma a into HA for a given A vector, right? Now, if you carefully find out sigma A square, here I was doing, which happened to be just a square into I. So that means I can say sigma A to the power of 2n as a like this, a to the power of 2n into I. Okay. So now, having this relation, and I can just find out what is the exponential of minus I sigma into a. Just whatever is here, I just include I inside the x and write the expansion. Okay, exponential expansion. Now, after writing that, I can separate them into two parts, right? Interestingly, the first part is just a sine function, and second part is the cos function. Okay, right? So that is what shown here. The first part is cos, second part is sine, right? So that is the unitary operator which I have for any given h. So now you know how to calculate the evolution operator, or it's also called propagation vector for a given energy of the system. So where energy could be a vector, okay? So energy could be a vector, okay? A, or it could be a scaled vector h bar. Okay. Now, so the particular case again, if somebody has some issues in understanding, I have done it neatly here so that you can go through. Now, sensing small signals. Let's get back. Let's say I have now probability with respect to time. So at every time I have calculated what is the probability. You know? So I can fix a time, I can change, okay? I can change what is the probability with respect to the signal strength V, okay? Right? So that is what, if I try to plot that, that also interestingly comes out to be a sinusoidal function, okay? Right? Because when I'm waiting in time or changing, like exploring the system in time means I am just changing the signal strength, okay, or bringing the signal near to the sensor or sensor near to the signal. In that way, the strength is changing. So that strength is changing, I can find out which happened to be sinusoidal function again. Okay, right? Now let me, this case, I have a curve, sinusoidal curve. This time it is a function of V. Okay. Now, if you carefully see, there are different slopes. There is a positive slope, there is a negative slope, there is a zero slope. Okay, there is a positive slope here. Okay, so I can choose particular locations where the rate of change of probability okay, would be connected to rate of change of signal strength. Basically, what I'm trying to do, delta P by delta V, I'm just trying to find the coupling factor, the gamma, right, from the curve. Okay, from the curve I can make, from the expression itself I can show delta P, the change in P would be induced because of change in V. So what is that? Change in V would add some extra phase. Okay, so that phase I have last time, I have gamma is equal to delta V by, sorry, delta P by delta V, right? So if I want to know what is the delta P, I just multiply gamma with the delta V, I'll get a delta P. Okay, so I have that extra factor I will be adding here. So omega is being replaced with omega plus gamma into delta. Okay, I have here. Fine. Fine. So now after adding that, okay, so you can just do some simple mathematics using some trigonometric relations again. And what you are going to find here is, okay, so the above solution, okay, takes a minimum value as a cost function becomes 0 at some scenarios, and sine function takes a maximum value at some scenarios. Okay, so you can show delta P would be very close to maximum slope at some point and zero slope at some point. Now let me concentrate at the close to maximum slope at this point. In that point, I can just show that the gamma into delta V into T is very close to 0, right? Okay. So in that case, sine of theta is just a theta. You just substitute as it is and get back what is the rate of change in P with respect to rate of change in V. The moment you know the change in P, you can make out what is the V itself. Okay, so that is given in the calculations like variance detection. Okay, so yeah, this is for your understanding. So for time being, we'll just skip this. Okay, so what I'm saying is, the moment you know what is a delta V, you can make out what is the V itself. Okay, please don't get confused with the V root mean square part. So what it connects is, the moment you know delta V, its variance from the some stable value would be equal to square root of square of root mean square. Okay, fine. So again, this is too much to expect to understand. But you can say the rate of change in probability would be connected to rate of signal strength. Fine. Now, so I would be thinking that I would make my experiments perfectly in all both the cases. I would expect the probabilities coming to be a single nice fractions. Like here, I'll get 0 with a one number and 1 with some number, where n0 plus n1 could be some equal to 100, like 1 probability wise. Okay. Now the question is that the case in the reality? Like let's say if I have a coin, if I toss a coin and I see if I make the coin flip 100 times and just to see what is the result out of 100. So ideally, I should be getting 100 out of 100, 50 heads, 50 tails. That is not the case. Okay. So there is always like a 46, 54 like that. Okay, that is very close to 50-50. But in this particular scenario, when I expect to get 0 kit and 1 kit, probably the outputs may not be exactly 0 kit, may not be 1 kit, very close to 0 kits and 1 kits. Other states are also possible. Those states comes because of the noise. Okay, so the probability distribution there, okay, would have a curves instead of a single lines. Okay, so that is happens because of the errors, right? So those errors one has to tackle. So what is this errors would be in the probability scenario? Would be some sigma p, right? As per the binomial distribution, which could be shown as 1 minus n into p multiplied by 1 minus p. Okay. For the slope detection, if I want to find the slope, the error at the 0.5, this is a 0.5 location, right? At 0.5 location, the errors would be, okay, 1 over 2 into square root of n. So that much error I would always make while finding the p. Okay? So that p would be carried further in finding what is a v. In this case, VRMS, root means square of the voltage strength, signal strength. Okay, so this is about quantum sensing for you. Okay, it's a lot of mathematics, I understand. Okay, I hope you people go through and you will understand detail. Okay, so okay, there is a question here. The probability graph should be a sine square. Okay, should it be? Yes, it is sine square. Okay. Fine. So what I have here is a sine square. So please don't expect absolute value of sine would have the peaks only on one side. Since it's just a sine square, I have peaks on both sides. Okay, so it's an exponential function. Sine is or it's a cosine function, so it do oscillate either side of the axis. Okay, right? You can cross check that later. Fine. So if you have any doubts, please let me know before going into the next part of the lecture series. Okay, I wanted to know how the initialization step has bearing on the final sensing effects. There is nothing actually. So, okay. So what you do in general is you prepare a quantum state, right? Okay. So what it means is electron existing in the ground. This is what the initial part, initialization of the system. So in the case of quantum circuits, what you see probably it might be like a taught already. So what you have is quantum resistors like that. So 0, 0, initialization things would go. Now I'll start with, let's say, harmonic gate and then followed by CNOT gate. Okay. So what do I get? I'll get here, I get at this point, I would be getting superposition state. Okay. Since it's a CNOT gate, since it's a CNOT gate, so what I'll get here, the output is 0, 0 plus 1, 1 square root of 2. This is the entangled state. Okay. This is a simple quantum circuit which gives me a bell pair. Okay. Similarly, whatever task I will be doing, I'll start the system from very initial form. So that is what the initialization. Later, see, this would not have sensitivity as much as any qubit. What is a qubit for me? Qubit is this. Okay. Qubit is this for me. What it means? It means if there is a quantum state, a quantum qubit, where electron is not staying there, is hopping between back and forth continuously, just like a fair coin being flipped. So if it is flipped, during the flip, it has both head and tail. So when it is fluctuating between 0 and 1, the electron can exist here or here with some probability. When I make a measurement, it exists there in particular probability. So that is what explained here in some mathematical form. So what I have to do, I have to start the system in very basic state, put that into qubit superposition form. Okay, right? Yeah, put that into superposition form. It could be equal superposition or some generic superposition, like alpha 0 plus beta 1, which is very sensitive to the external field, because the external field could enhance the orbits and increase the oscillation energy, or increase the separation, or while it is just doing oscillations, the external field can just stop oscillating and it just impose transition to the ground state, relaxation. So how much this external impact is causing on this superposition, I would know by exposing this to a unitary operator, where unitary operator is actually exponential minus I total Hamiltonian into T by H cut. This is the unitary operator. So this would leave me some quantum new state. Okay, right? Or you can call it as a psi 0, and this would be psi of t. So this, by studying this psi of t, I'll find what is chances of getting 0 when I make a measurement. I'll get what is the chances of getting 1. Okay. So with the probability, which is comes out to be an oscillatory function, which I have, which is oscillatory in time. Okay, it is also oscillatory. Okay, different oscillatory. This may be different. This is may be different frequency wise, and I would get probability in the strength of V. Okay, right? So the moment I know what is the function would look like experimentally, I can easily make out what is the V strength. V is actually made up of. Fine. So that is what I have for the sensing. Fine. So can this sensing method work for degenerate states? Yeah. Okay. What do you mean degeneracy? Yeah. So degenerate states in the sense. Okay. What is, first of all, what is a degenerate state? For example, I have a Hamiltonian, right? It possesses eigenvalues, let's say lambda 1, lambda 2, and corresponding to each eigenvalue, I have a eigenvector E1, E2. Okay, I'm sorry. Yeah, so this is active file. Okay, now what does degenerate mean? Degenerate mean there exist matrices where corresponding to same eigenvalue, there may be multiple eigenvectors. Okay, so in this particular situation, that means you are talking about there are states which are having same eigenvalues, but they are different in the state wise. So probably no, I would say that situation degenerate states I can't use for the sensing, but the sensor, the signal which is coming, probably multiple signals with the same strength could have same state. Okay, what I mean is the H overall consisting of HV, right? Okay, HV. So V, what I'm writing here, could be combination of some V1 and V2s. This could be electric field. This could be magnetic field. Okay, or electric field of, this is electric field of one particular charge, let's say Q1, this is a particular Q. Both happen to be same strength wise. Okay, so in that case probably I can easily detect here. Okay, but I need to have the energy states are specifically separated for the quantum state to have a sensing effect. So that is the one of the criteria need to be satisfied in the case of system to set the system to become a sensor. Okay, the Difference-Injo criteria which I discussed yesterday. Okay, fine. So is there any other questions before going further? Okay. Can use H gate always or some other gate? So H gate is it has an effect of creating superposition. What I mean is, if the electron is in the ground state, means the system is the quantum state, initial state is like this. If I want to become a superposition, if I want to put that in superposition, okay, so I have to send this quantum state through H gate. So in that way, the new state would become a plus state, equal superposition. How it is done is, I am sending a pulse of photon. The area of the pulse is actually pi by 2. Okay, this pulse of photons, it will go, and each photon, one photon, the energy of that photon matches with this separation. The one photon raises the electron there. The electron would stay there for some time, let's say microseconds, because that is the lifetime. It tries to come back because it can't stay there, it will emit the radiation and comes back. By the time it tries to come back, one more photon is there, no? It rises. So in that way, it is just like the bunch of photons would try to put the electron to go back and forth. That is what the superposition is all about. Okay, the Hadamard gate is actually doing that job experimentally. Okay, right? It's a simple pi by 2 pulse acting on the atom. Fine. Okay, so now any more questions? Do we need to determine the probabilities to do the sensing? Yes, of course. That is how the actual sensing is done. Here you see. Okay, this part. So quantum states is like when you are working with the quantum states, basically, so there is a final output state is there. So it is actually having some superposition states. Okay, some x superposition, some superposition of some x and y. Okay, right? So how do I know how much x is there, how much y is there? So I have to put that under measurement kit. When I put the measurement, I'll get the information how much x is there, how much y is there. So it's all about measurement. It's all about the finding the probability of particular output. From there only we can make out what is the output state made up of, and which is actually started with something, becomes something because of external signal. How much it got changed, I just convert this output basis to the known basis which I have 0 and 1. Then I would know, initially I started with the zeros, how many zeros I ended up with. I don't have ones. Now new ones have come up. How many ones have I come up? From there, the change, what is it undergone, is exactly proportional to the what is the signal strength. Okay, so alpha directly proportional to the, so it's not alpha, it's proportional to the V of t. By knowing the probabilities, I would make out what is the signal strength. Okay, fine. Okay, do we need to determine probabilities? Okay, next, any more questions? Let me see. Yeah. Okay, so looks like no further questions. We can start the next part. Okay, so yesterday I was telling you about the intended plan for this Friday lectures on quantum sensing. Okay, so the first one is the basics of quantum sensing. This is like, so we have concluded that by now. Okay, now the next one is basics of single or entangled photon emission. Okay, I want to know what is a single photon emission or single photon emission or entangled photon emission. When I say entangled photon emission, what I mean is the multiple photons. So we can start at least by 2 photons. How 2 photons are emitting, which not just two, entangled by nature. Okay, so to go there, we need some mathematics. It's the basics, right? Basics. The basics I want to understand. So for basics, I need to go some quantum mechanics fundamentals. Okay. So for that, I would just introduce for the most of the computer science people. I hope if they may have come across, or for other branch like electronics, probably they might have seen, or even mechanics people also have seen. So what I'm going to introduce is a simple pendulum, a very simple. Okay, I have a pendulum which is tight, just makes an oscillations. Okay, so pendulum, it's by nature it's called a simple pendulum. Simple pendulum. Okay, and it's also called harmonic oscillator because it is nicely making harmonic oscillations. Right? Now, why did I bring this pendulum idea is, if you just take anything in the universe, okay, everything is actually disturbed by its equilibrium position and it is making oscillations about its equilibrium position. That is what I have here. If you see, okay, to see here, I have a pendulum. If I don't do anything, because of gravity, it stays in the equilibrium position. This is the equilibrium position. Now I just push it and give some amplitude. I'm disturbing about its equilibrium point and let it to evolve in time. So if I do that, it just does the oscillations. Okay. So oscillations is in a way like making one rotation. So once it goes, makes half a rotation. Once it come back, another half of the rotation. Okay. So everything is like an oscillation. You can just start with nucleus and electron. Electron is oscillating or rotating about the nucleus. Okay, and something vibrating. There is a crystal structure vibrates. It's called phonons. So everything is oscillating about some equilibrium position. Even if you just take electromagnetic wave, okay. So there is an electromagnetic wave. If I say there is an electric field vector oscillating. So the electric field amplitude, this is amplitude. Okay, electric field vector is usually written as E naught sine kx minus omega t, which is propagating along the x direction, E of x. Okay, so the electric field amplitude is maximum, decreases, and then becomes negative, and then again decreases negatively, increases positive. So this is electric field vector oscillating, and this is on the vertical plane. If you just see on the horizontal plane, okay, the magnetic field vector is oscillating, which is magnetic field vector is, just a minute, magnetic field vector is B is equal to B naught sine kx minus omega t. Okay, now so here something which is oscillating. You see, initially, what is this? Prevent this page creating additional angles. Yeah, I think. Wait a minute. Let me start a fresh one. Okay, so always electric field vector is oscillating. So electric field vector maximum small 0 and maximum in negative, and then magnetic field vector in the horizontal plane. So propagating is happening, let's say, in the x direction. Okay. Now, if you carefully look at it, electric field vector is oscillating. So I can just connect this to a pendulum, which is oscillating, by the way. Okay. Now, the electromagnetic wave is quantum by nature. It's having photons. So I would say, if I had to connect this, it has to be quantum harmonic oscillator. Okay. Quantum harmonic oscillator. Okay. So just to study anything which is vibrating or oscillating, I would use a simple harmonic oscillator, a pendulum. Since it is quantum in nature, so small in nature, so I have to use quantum harmonic oscillator. So what is this quantum harmonic oscillator is? It is just like a simple pendulum at a very quantum, tiny level. Okay. So for me, what is a pendulum? What is a pendulum? Pendulum has a kinetic energy when it is oscillating. If it is not oscillating, it will have potential energy. Okay. So potential energy here, if it is raised from the floor, okay, this is a floor, it will have some potential energy depending on the height, m, g, h, mass of the object, gravity, and how much it is raised. Okay. Since I am taking a reference point here and I have lowered from the reference point, okay, so the pendulum would have some potential with respect to here. Okay, so that is a potential for you. We can find that. Now, it has a kinetic energy. What is the kinetic energy? Is simply half m v square. I just multiplied by m and divided by m, which becomes mv whole square divided by 2m, which is linear momentum square by 2m. Okay, so kinetic energy is this. Fine. So potential energy, how do I know potential energy? So potential energy is actually created here because of the gravity. Potential energy is what? The system wants to come back to equilibrium point. When I disturb it, it tries to come back. It can't stay there for some time because of this inertia of motion. It goes back high and then it does some oscillations. Every time it decreases, after some time it comes back to its original position. It is simply like if I have a spring mass system where if I just stretch it by some amount and it just makes an oscillations. Okay, why is this making oscillations? Because the inner ability of the spring to come back to its original position, so which is actually coming because of the restoring force. The spring constant is k minus k into x, how much it is being stretched, that is the restoring force. So force is actually connected to the potential of the system. What is that is? The potential of the system is actually equal to force, restoring force is actually equal to the way potential energy change with respect to space or variable along with it is changing in a negative way. So there is a negative cancels. dV is equal to kx into dx. If I integrate, I would be getting potential energy of this particular spring mass system is equal to half kx square. Okay. Now, when I'm just doing stretching, means I'm applying some force. Okay. So let's say that force is there, which creates some acceleration, Newton's second law that we seen yesterday, which I can write it as m into d square x dt square. Okay. Now equate this m d square dt square equal to what is the force, by the way? Force here is minus kx. So you just simplify this equation into integrable form, which is d square x dt square. Let me ignore the vectorial form for time being, plus k by m into x is equal to 0. Okay, so this, it will have a sinusoidal solution, which is, okay, sine omega t, where omega is root of k by m. So k is what? Spring constant is actually in this particular situation, okay, is equal to m omega square. Okay, so k is m omega square. What is the inner potential of any given oscillatory system is half kx square, right? So you just substitute in place of k m omega square x square. Okay, so always internal energy of the oscillator system is half m omega square x square. Now for the spring constant, I usually people give what is the spring constant. Let's say if somebody has not given spring constant, that would be this one. Okay. Now, if I have to write the total energy of the system classically, which would be P square by 2m kinetic energy plus half m omega square x square potential energy. Okay. But I am not concerned about the total energy of the classical system. I am concerned about the quantum system. So where the total energy would take an operator form, which would I will put hat, momentum operator becomes momentum label becomes momentum operator, x becomes x operator. Okay, what is the difference? P can take operator form in one dimension, and x would just take a multiplication with the x value. Okay, so this is a Hamiltonian for quantum harmonic oscillator. Okay, so this is what I want, because this is represents something oscillatory systems, represents oscillatory systems. Since my electromagnetic wave is oscillatory, okay, it is oscillatory, I would use the harmonic oscillator concept to understand what it is consisting of. The moment I know what is oscillating, what is the energy coming out from the electromagnetic wave, I would understand possibility of getting a single photons or multiple photons. You see, so that is a basic thing, right? So to know a possibility of realizing a single photon source or multiple photon source where the entanglement is possible, I first know what is the energy consisted within the electromagnetic wave. Okay, so electromagnetic wave is basically, electromagnetic wave is like there is a positive dipole, a pole, negative pole, together it creates a dipole. The dipole is actually oscillating. The negative positive pole comes closer, negative pole comes closer, and they come very close, they can't stay very close. After some time they go back. So basically they are actually oscillating near away, and they emit the radiation because of that. That is what the electromagnetic wave is. Oscillatory dipole which creates the electromagnetic wave. So I want to know how this could be understood. The moment I understand, then I know how to produce. Understanding would give me the idea of realizing single photon sources. Okay, so I can just simply say there are multiple photon sources, single photon sources are there, these are theirs, this produce, this doesn't produce, that's all. There is nothing basic in it. It's just like a company manufacturer giving you the device information. Okay, fine. Now let's get to how harmonic oscillator could be useful and understanding the electromagnetic wave. Okay, now Hamiltonian is there. The Hamiltonian is there. Now, like continuation from the yesterday's class, the moment I know Hamiltonian, it's a matrix. So Hamiltonian matrix comes up with its own eigenvalues, eigenvectors. and eigenvalues, like any matrix. Okay, by knowing the different eigenvectors or eigenstates people call, knowing eigenvalues, corresponding eigenvalues, I know some information of the system. Okay, so if somebody gives me a matrix, I can easily find the eigenvalues and eigenvectors. Somebody gives me, okay, somebody gives me h in the form of the expression like this. Okay, so what is it? It would be converted if I convert p to minus ih plus dou by dou x. The Hamiltonian would become p square. Sorry, Hamiltonian would become, okay, minus my this Hamiltonian would become minus h square by 2m dou square by dou x square quantum state in continuous form, not in in form of Dirac notation. Okay, m omega square x square psi of x is equal to e into psi x. So here you see this is a Schrodinger equation, time independent. Okay, because I don't see any specific time here. Okay, so now to know the system in detail, I have to solve the second order differential equation. Second order D is very tough. Okay, so for that, what I can do, I can just look for some algebraic method to solve this equation. So use algebraic method to solve. Okay, so which involves something called operators, which are annihilation. Will come what is annihilation, okay, and creation operators. So which is represented as a dagger, a dagger operators. So these are actually non-Hermitian. Okay, non-Hermitian. You guys know what is a Hermitian? Okay, right? So let's see how it is done. Now, if you just carefully look at the Hamiltonian here, Hamiltonian itself is very, very complicated, very written. So can I simplify that? Okay, so how do I simplify? Let's say I introduce new terms which are Hermitian. Okay, so in such a way that I introduce a new momentum operator, scaled operator, in terms of old operator divided by square root of m omega h cross, and q hat is equal to position operator multiplied by m omega by h cross. If I introduce these changes, okay, which is actually p square, capital P square is equal to small p square into m h omega, and x square is equal to q square h by m omega. If I introduce these changes in the Hamiltonian, what you get, just let's see cross check, I'll get p square, okay, m into h cross omega divided by 2m plus 1 by 2 m omega square q square, okay, and h cut divided by m omega. Now I can cross few terms, m here, m there, omega here. Okay. So what I am left with, if you carefully just simplify, what I am left with is h omega on both the terms, 2 is on both the terms. What I'll get is, put hat every time, don't forget, because it's a quantum systems. Okay. See here, the moment I just changed the capital P to small p, okay, by introducing some scaling factors, okay, right? Remember, P is a Hermitian, uh, and small p is also Hermitian. In that way, I have introduced. Now, I just got rid of the so many extra factors which were there in the Hamiltonian. Those things were reduced to some smaller section. Now, still I have second order terms. So P and Q, small p and small q, they're still the operators. So they're in quadratic form. So I want to get rid of that also. So this time, trick I'll follow is, let me introduce a non-Hermitian operators. Non-Hermitian. What I mean is something which are not equal to a dagger. Okay. If I introduce non-Hermitian operators, which is like, let me introduce a is equal to q plus, q minus. You can start with q plus also, that doesn't matter. Q minus ip, and a dagger is q plus ip. Okay, so these are definitely non-Hermitian. Okay, so if you introduce this way, like I said, if you want, you can introduce plus here, and you have to stick with that same thing. Plot doesn't matter. Okay, if I introduce this, now from here you can say, so this is a dagger. I'm sorry, a dagger. Okay, complex conjugate. A is a dagger. Okay, complex conjugate and transpose. Now, if you see a plus a dagger is equal to 2q, and a minus a dagger is equal to 2ip. Not only that, there are some other relations also you can find out. There is a very interesting relations, which are, if you just try to find a dagger multiplied by a, which is half q minus ip, sorry, q plus ip, 1 by, so just a minute. I have a factor 1 by square root of 2, 1 by square root of 2, which is missing. Okay, and this is 1 by square root of 2, 1 by square root of 2. If I have 1 by square root of 2, 1 by square root of 2, so it will comes out to be 1 by 2 overall multiplied by q minus ip. Okay, now this is equal to 1 by 2 q square plus p square minus plus I into qp minus I into pq. Okay, so in quantum mechanics, if there is a two operators a and b, if I just put in a rectangular bracket, what it means is ab minus ba. When this rectangular bracket is equal to, means a and b are commuting. The commutativity holds good between them. Okay, fine. So here, what I have, the last two terms is actually equal to the commutator bracket, which is q square plus p square plus I by 2, okay, into commutator of q with a p. Now, what is this q with a p commutator? You can easily find by substituting what is a q. Q is what? I have introduced earlier. Okay, so q is this term. What is a p? P is this term. Okay, by substituting explicitly, you can find the commutator of q with a p is actually equal to IH cross. You might be surprised to know that how q and p becomes YH cross, because remember, when I have a capital P, which is actually taking minus H cross dou by dou x, capital X becoming just a simply X. If I want to find what is the P into X, which is equal to minus IH cross dou by dou x, acting on X, which is just a simply minus IH cross. Okay, the other way around, X into P, if you want to find, which is like X multiplied by minus IH cross dou by dou x acting on 1, which is equal to 0. So if you just introduce that, basically it is a product of px and another term xp, which gives you this. Okay, you can cross that, it is there in the notes. Okay, now that relation is established. Okay, and now interestingly, having known that, if you just substitute that value here, okay, what value? IH cross, sorry, what is the value? IH cross. If you substitute here, what it comes out to be is A dagger A is equal to, okay, 1 by 2 square root of q square plus p square, regular bracket, plus, sorry, minus 1 by 2. So we send this minus 1 by 2 to the left. Okay, so what I get is half q square plus p square is equal to A dagger A plus half. Okay, so that means the Hamiltonian would become h omega A dagger A plus half. Simplified. Now the second order terms are disappeared and I have a product of two non-Hermitian operators. By the way, I know some information about the non-Hermitian operators. What is their product? What is their sum? Those things I am just trying to find out one by one. Okay. So one more thing here, you see this A dagger A, which I have here, I can name it as something like a number operator. Okay, what is the why I'm calling a number operator? Because this number operator acting on some states, okay, some quantum state would tell me how many particles are there, quantum particles are there, how many are there in it, or when it comes to energy, how many photons are there in it would be knowing when I act this onto some quantum state. So that is the role of this number operator that we will establish as we go further. Okay. Now talking about the A and A dagger, let's just check what is the commutator of A dagger. Okay. So interestingly, this comes out to be, okay, A dagger comes out to be 1. Very, very interesting. And A into A dagger, we know A dagger A is n. A into A dagger is simply equal to 1 plus A dagger A, which is actually 1 plus n. From here I can get that. Okay, so this is another interesting results. These are like algebraic results which I will be needing. Now, why I will be needing? Okay, we'll see it as we go further. Now, let's say H is simplified into n plus half. Okay, n plus half. Now, if you see carefully, n is integral part of H. So n is consisted in H. So that means it's a matrix H is created out of n by adding some 1 by 2 identity and scaling by some H cross omega. So that means I can say H and n commute itself, both of them. So whenever two matrices commute, means they do possess common set of common eigenvalues and eigenvectors. So let's say there is a common set of eigenvalues for n. So there is a eigenvalues for n like this. Those eigenvectors happen to be eigenvectors of H also because of the commutativity, which is equal to some En. Okay, right? Eigenvectors would be common, eigenvalues would be different. Okay, maybe I should remove that. It might confuse. Common eigenvectors would be there. Okay, so there is a different eigenvalue, different eigenvalues, but eigenvectors are same. Now, having known that, let's just try to find what is this En is all about. Okay, so for time being, let's find out what is the action of H on the n, which is equal to H cross omega by 2 n plus 1 acting on here. So which is equal to h omega by 2 n plus 1 into here. Okay, what it says is En is equal to, I'm sorry, I just missed something. Okay, okay, a factor of half is actually inside, not outside. I'm sorry. Yeah. So this factor is inside. Okay. Fine. So h omega multiplied n plus omega. Okay, which is the energy of the particular energy of the quantum state. Okay, so H would have eigenvectors, corresponding eigenvalues are like this. So it is like 0 ket, 1 ket, 2 ket, 3 ket, and 4 ket, and so on for harmonic oscillator. Okay, so what is the separation of energy? If I cross check, which is going to be H omega. Okay, a fixed energy separation. Now, so the energy eigenstates cannot go negative. So the n is at the most can be 0, but negative values not possible. Okay, because negative eigenvalues are possible for the n matrix. Okay, which is A dagger A, which is Hermitian by the way. For the Hermitian matrix, okay, complex eigenvalues could be eliminated, but n cannot go negative. That we will see in the later part also. Okay, now having the information of the energies of the harmonic oscillator, okay, let's try to get a little more. Okay, fine. So at this point, let me go to my lecture notes. It's quicker. Okay, so where we are at. Okay, so 37, 337. So I have to hurry. Yeah, right. So we just went up to here. Okay. Now next, let's try to understand what is the physical significance of A dagger, and N operator. Okay. So it's all about finding whether they're commuting with each other. If they're commuting, what is the nature? Okay. So let's try to find out whether A vector does it commute with H. Okay. So does it? And let's try to find out. Okay. Now, if I just substitute explicitly what I have here, okay, what I have here, and then exactly see H omega A into N minus N into A, right? So, in fact, what I have A dagger is equal to 1 plus N. Using that relation, I can show that A with the H commutator is actually H omega A. A dagger with H with commutator is minus H omega into A. Okay, so that is very interesting to see, right? Not only that, you can just see using those two relations, I can show that if I am constructing a new quantum state by acting N on N operator A, okay, that can be a potential eigenvector of H, okay, with what eigenvalue? Just an eigenvalue which is reduced by minus H omega. Okay, how did I get that? Using whatever relations I have obtained from there, I just got that. Okay, So let's go to the another situation. Let's check whether the quantum state n of harmonic oscillator acted by a dagger, will that be a eigenvector of h? Just cross check and substitute whatever relations which you obtained so far, and you see, yes, that is going to be eigenvector of h with the eigenvalue slightly raised by n with h omega. Okay, that means a and a dagger, which I have defined norm emission operators, which raises the given quantum state of harmonic oscillator by a factor of h omega in the case of a dagger. In the case of A, which is lowers the energy by h omega. You see? Okay. So that means A is called a creation, A is called annihilation operator, A dagger is called a creation operator. Or you can say A and A daggers both are ladder operators. They just raise the system. If this electron is here, if I add a dagger on this particular state, electron is risen to the next level. Or if I add a dagger, sorry, A on this, so electron is pushed to the down. Okay, I'm talking in terms of material. If I'm talking in terms of energy, if there are two photons in this state, if I add a dagger, means I'm adding one more photon, push the number state to the 3. If I'm acting A on that state, A matrix or A operator, that means I'm trying to reduce the number of photons from 2 to 1. Okay, so that is the idea. Fine. So I have established that. Fine. So now, if you just carefully try to find out, is there any, see, A is a matrix for you. Okay, A is a matrix, and A dagger is a matrix. Okay. So do they possess their own eigenvectors? Are they? Let's try to find that. Okay. So A acting on an, I just got to know its energy is reduced, the photon numbers are reduced by 1. A dagger acting on the system raises by 1. Okay. So basically, I can represent the new state by either n minus 1 or n plus 1. When A acting on n reduces by n, reduces to n minus 2 get state. Okay. And if I just take inner product of left hand side with itself and inner product of right hand side with itself, what I would be getting is, okay, what I would be getting is the n operator inside, and that sounds so this goes to where, let's say I don't know what is a Cn, so the Cn could be easily found in terms of square root of n. So where it could be positive or negative. For the time being, we just take positive cases. Okay. So the A reduces a quantum state by -1, and it has to be multiplied by square root of n. That means the n's cannot be eigenvectors of A. If I want to have eigenvectors, both sides I should have same vector with some eigenvalue. That is not matters. Okay. Now let's find out A dagger acting on n. Let's say I know that it raises the state by 1, but I don't know what is the factor I have to substitute here. Let's say, let me call Cn. Again, let's take the inner product of left hand side with left hand side, right hand side with right side, and try to find out what is Cn. Cn happened to be square root of 1 plus n. Okay, so literally, again, quantum states n, the harmonic oscillator states, cannot be eigenvectors of A dagger because I am getting two different vectors on both sides. But I could use this relation later on, which is very, very important. Okay. Now, I just know eigenvalues of our H matrix, that these are the eigenvalues. Now the question is, eigenvectors I know, n kets, okay, so which could be 0, 1, 2, 3, and so on. Now, is there any provision I can get to define some new quantum states, okay, which could be used to describe electromagnetic wave. Okay. So now, interestingly, what you observe is if I start with 0, at a plus, I'll create 1. Again, at, I'll create 2, 3, up to n. So that means what? N I can simply write in terms of acting a dagger several times on 0. Okay. So there is a scaling factor of 1 by square root of n factorial will come, so that you can work out just by looking at the mathematics. Okay. Now that is one thing. Okay. The next thing is, even by acting A on n, I would create eigenstate of H. By acting A on n, A dagger on n, also I'll create eigenvector. Okay, fine. So now let's come back to the whatever harmonic oscillator information which I gathered. Let's try to put that into use for the case of electromagnetic wave description. Now, in the electromagnetic wave description, I just said there is a oscillatory functions taking place. Like electric field vector is oscillating because of the dipole, electric dipoles, and magnetic field vectors is oscillating in another plane. Okay, so now that means I can bring the harmonic oscillator idea here to represent electric field vector oscillation and magnetic field vector oscillation. That is what I will try to do. Let's use that. Okay, now one thing, let me get back to my notes. Okay, now electromagnetic wave means it could be a standing wave between 2 points. I just create a standing wave pattern. Okay, so it is just like if I have two rope is tied between 2 points, I create a wiggle, it creates a standing wave pattern. Okay, I'll ask somebody to create another wiggle, so he would create a wiggle such a way. Okay, so there the number of wavelengths confined between the lengths, let's say 0 to L, is different from my standing wave pattern and his standing wave pattern. Okay, so in quantum systems, there is nothing certain, everything is probabilistic. When I say electromagnetic wave means there are so many possible standing wave patterns inside. So which are called modes. They are called modes. Okay. So let's understand classically what is the modes, right? For example, if I just take two pendulums, okay. Okay, just a minute. Just take a two pendulums. Okay. So these two pendulums can oscillate in various ways. Both the pendulums can come to left and go to the right. Let's say that is one method or mode of oscillation. Both together. Okay. And in other case, one goes to the left, other goes to the left, right. So this is left, this is right. That is mode 2. Right? So I am able to, with the two-dimensional system, I am able to create two modes of dynamics. Similarly, electromagnetic wave, like I said, the wavelengths confined within a range of 0 to L, there may be different kinds of modes existing. So one may be like this, another may be like this, okay, another may be like this, right? So that means there are so many modes, mode 1, mode 2, mode 3, okay? So those modes are like eigenstates. Each mode would have its own energies, okay? So that means I can represent the Hamiltonian corresponding to the electromagnetic wave in such a way that if I try to find eigenvalues and eigenvectors of that Hamiltonian would correspond to these modes beautifully. Okay, let's try to find what is a Hamiltonian with respect to electromagnetic wave. Now, Hamiltonian means what for me? It's a kinetic energy operator plus potential energy operator. Okay. So for electromagnetic wave, what is it? What is that? So you can just simply show. Okay, let me get back to my notes quickly. I can right. So electromagnetic waves means what? Electric field vector is there, magnetic field vector is there. They exist in the free space. They are oscillating in free space. The electric field vector may be created out of some charge density, and magnetic field vector is created of some current density. Okay. Now the Maxwell's equations would tell me how electric field is created from the Gauss's law, and magnetic field is created from Ampere's law. This is Ampere's law. The curl of B is Ampere's law. Gradient, the divergence of E is Ohm's law. Okay, right? So this way, I would find electric field and magnetic field. And there is other thing. Other two equations are there. One is divergence of B is 0, and a curl of E is minus time time derivative of B. What they are actually conveying is divergence of B is equal to 0 means magnetic field lines would never cross each other. Okay, right? And curl of E means non-zero curl of E means magnetic electric field lines could curl when there is a rate of change of magnetic field. If the magnetic field is not changing, even the curl E is also 0. That is what they convey. Now, this is all the four equations are called Maxwell's equations. Now, I can just play around with the Maxwell's equation to obtain something called a wave equation, because wave equation is something which tells me how the disturbance travels in the space. Okay, right? So here in this case, I just take the curl of E equation. I take the curl of that entire equation. So that is what it gives me. Okay, it gives me this part. The curl of curl E is equal to gradient of divergence of E minus gradient square E equal to minus dou by dou T. Curl of B is actually here. Let's say I don't have charge density, I don't have current density. Substitute rho equal to 0, J equal to 0. I'll get back this equation. Now, just by gradient of divergence of E is 0, this term is not, this first term will not contribute, only second term would contribute. And the other side, I have this term. By just doing the rearrangement, cancelling the negative signs, I would finally get to this equation. This is actually wave equation for electric field vector. And similarly, I can get wave equation for magnetic field vector. Okay, right? Now, this is a second order differential equations for E, second order differential equations for B. Okay, so easily you can find the solutions of this kind of equations in the form of sinusoidal functions, which is written here. Okay, fine. Okay, and similarly for a B. The only difference from E to B is E would exist in X plane, in X axis, B would exist in Y axis, because they have to be orthogonal to each other. Okay, so B has to be a cos function, A has to be a sine function. Okay, so I have corrected here, I have not corrected, please note that change. Okay, now I can simply find what is the total energy which could be saved in the form of electric field and magnetic field. Okay, so which is actually comes from a Poynting vector expression, but here I'll simply write down the total energy stored in terms of electric field would be half into exponential E square. Magnetic field is half into 1 by mu naught B square. In a small volume, that much energy can store. If I want to find some large volume, some total volume, I'll just integrate in volumetric. So dV stands for small volume element. Okay. Now I know what is a H. Next thing is I I can find the eigenvectors of H or eigenvalues of H. By the way, I don't know what is the operator form for electric field and magnetic field. Okay, so what I'll do, I'll try to express the electric field and the magnetic field, okay, in terms of the operators which I know. I know the Q operator, I know the pre operator. If I substitute with some scaling factors, you can cross check what are the scaling factors later, which will involve omega, the frequency of the electromagnetic wave, and this V is a total volume, epsilon naught is a permittivity of a free space, mu naught is a permeability of the free space. What they actually describe is whether electric field lines can go through the free space smoothly or not, described by epsilon naught. Whether magnetic field lines can go through the free space or not, described by mu naught. Okay. So if I substitute E and B in terms of Q and P, which I know earlier, I would reduce the Hamiltonian into, again, small quadratic form. I hope you would now appreciate why did I introduce harmonic oscillator, quantum harmonic oscillator earlier. Now my H of the electromagnetic wave become harmonic oscillator equation. I'm sorry, I'm only talking about a single mode now. I am not talked about all the modes could exist in a harmonic oscillator. Okay. Now I have a quadratic terms just like I did for the harmonic oscillator. I want to reduce quadratic to linear terms. What I do, I introduce creation and annihilation operators. Okay. So how did I do? I just convert P and Q's in terms of annihilation and creator operators, just the same way I did in the previous case. Okay. P would be sum of A dagger. Q would be A dagger minus, sorry, A into A minus A daggers. If I do that, I just reduce the overall Hamiltonian into much simpler form what I had earlier. The moment I do it, it is straightforward. I can just say whatever eigenvectors this Hamiltonian would have is just similar to harmonic oscillator, quantum harmonics and harmonic oscillator Hamiltonian. Okay, so once that is done, okay, what I will just say for many modes, what is the total electric field? Okay, which would have some summation over the modes, lambdas, and magnetic field is also summation over lambdas. That means Hamiltonian would also be summation over many modes. Okay, wherever the operators are, you put the subscript for the mode and finally obtain the corresponding eigenvectors for the total Hamiltonian of the electromagnetic wave, which is simply the quantum vectors eigenstates n lambdas. Okay, right? So the n lambdas are just like the n cats which I had even for the harmonic oscillator. Okay, and now I just conclude for today. What important information which we gathered here is, if we just try to find what is the expectation value of the n vector, okay, the number vector for the particular lambda mode, which is some number, okay, and let's say that the expectation value is average in the value. In general, I'll try to find how many photons are there in a particular mode, and that would comes out to be n bar, average number. Let's say how each state would vary away from the expectation value. Let's say there are various modes, right? There are various modes. This mode would have, let's say, 5 photons. This mode will have 7 photons. This mode will have 3 photons. Let's say the average number is 4, number of photons wise. So this is deviating from the average value by 1. This is deviating from 3. This is deviating by 1. So there is a deviation from the average value. What is the deviation if I just try to find the deviation from the average value? And what is that? The average, so the deviations, expectations, if I find, okay? And not only that, if I find the deviation square expectations, which is happen to be variance, which is actually 0. What it conveys is, if I happen to put the quantum systems of electromagnetic waves in particular state n lambdas, okay, if I put them in n lambdas, there is a very good chance that would keep intact the number of photons it can have. Okay, so what I mean, let's go to that final slide for today. Okay, if I prepare a, let's say if I prepare a quantum state of electromagnetic wave with a particular mode staying with one photon, it stays there ever until it is disturbed in one photon state. Means it is rigid for external means or some eavesdropper. So I prepare my information in one ket state and use that for quantum channel communication for quantum key distribution. Probably quantum key distribution is discussed earlier today, so earlier in the previous lectures. So that is what you can do. That means the n ket states which I have discussed so far, they are actually known after the scientist Fock. They are called Fock states. So these Fock states are rigid or less prone to the external means, so that they remain intact when they are prepared in particular number of states. If I prepare a system in one photon state, they remain in the one photon states. So that is what we had discussed so far. In the next class, we will discuss a little bit about the photon statistics and correlation about our correlation parameter, which describes whether the system, like a photon sources, emit photons in single photons or bunch of photons or not. That we will discuss with whatever information we gathered today. Okay, right? So let me summarize overall for today quickly. So just to understand basics of single photons, we want to use the quantum harmonic oscillator picture to describe the energy, to describe the how electromagnetic waves are actually behave quantum mechanically. Since they behave like harmonic oscillators, so I just brought in the harmonic oscillator description. Okay, they're simple extension of classical simple pendulums into quantum regime, like a quantum level. Okay, where I can write the Hamiltonian in terms of kinetic energy and potential energy, and their kinetic and potential energy takes operator form, right? So the Hamiltonian is very complicated. Second order differential equation would be arises when I try to find eigenvalue equation there. I have to convert the Hamiltonian into much simpler form, this like putting all the scalars into some factors. So I just introduce Hermitian operators small p and q, and then Hamiltonian is reduced further. I am not satisfied. I want to go much simpler. So I'll introduce non-Hermitian operators a and a dagger. By doing it, Hamiltonian becomes now a simple number operator with a plus sign, with a plus half multiplied by h omega. So with that, I can easily find what are the eigenstates and eigenvalues of Hamiltonian. Eigenvalues are just h omegas with the n plus half multiplied to it. So, and eigenstates would be just a number states, 0 and 1 and so on. Okay, right? So interestingly, this number states what I have are rigid because they don't have variance. So that means if I happen to prepare them in the particular number state, they remain the same number state, even some eavesdropper tries to touch them. Okay, so we'll discuss the details of how the photon statistics of this number states would give more information about whether the given photon sources are single photon sources or multi-photon sources or something called coherent sources are not. That we will discuss in tomorrow class. Okay, right? So again, it's a lot of mathematics. Okay, please do touch the lecture notes and read through, and you would definitely understand. I would guarantee that. If you go through line by line carefully, you would 100% understand. Okay, so let me see some questions here. Okay, is variance always zero? No, not for every case. Only for the number states, variance is zero. Okay, the number state means cations. Okay, y minus sign, I don't mean where, somewhere it is. You go through the notes, you will understand that. Will this lowering and raising operators work as a gate? Yeah, definitely. They're like a gates. They are like a matrices, right? So that means they are okay. One minute. So for a quantum gates, one condition is what? They have to be unitary. Okay, and just check. A is a matrix. A dagger, is it identity? No. So they cannot be a quantum gate, but they can be a quantum transformation matrices. Okay, right? So they cannot be quantum gates. Remember that. They may rise the number state to higher or reduce to lower, but the quantum states means what? The quantum gates means what? U dagger must be identity. Okay. A dagger is not identity, or A dagger A is not identity. So they are not unitary by nature. That means they cannot satisfy, or they may satisfy the condition of a quantum matrix. So quantum matrix gates. Okay. So okay. So when we talk about Maxwell equation, are we not touching the classical concepts? Very good question. Okay. Yes, so there is something called semi-classical physics. Okay, semi-classical physics in the sense I have a material interacting with the radiation, where I can choose the material atom to be discrete, means quantized, having energy levels 0, 1, 2, 1, 3, and radiation which is coming may not be in the form of photons. It may be continuously varying. So in that way, we can study the interaction of radiation with the matter. That's semi-classical physics. If I treat even the radiation also in the form of discrete energies like a 0 kite, 1 kite, and so on, the way we did it, it is pure quantum. Okay, so the question you are asking is, when we talk about Maxwell equations, are we not touching the classical concept? Of course, yes, you are absolutely right. Okay, so I started with the classical concept. Okay, right? Where are we? If you just see, right? So this is a classical energy. I have not brought in any discreteness here. Electric field vector is there, magnetic field vector is there, varying continuously, varying. Okay, then I introduce energies, sorry, electric field and magnetic field in terms of some quantum operators Q and P, where Q and P further are combinations of A and A daggers. Okay, so I'm just converting or transforming from classical physics to pure quantum physics. So by the time I come for the final state, let's say here, if you see electric field and magnetic field vector, what I've shown here, they are expressed in terms of A daggers. So they have become already pure quantum. Now, having that, now just try to find what are the energy states of that particular Hamiltonian. They're discrete. N kets, N lambda kets for a particular lambda, lambda stands for particular polarization or particular mode. Okay, lambda would have many modes, na? Okay, so here the energies are discrete. Okay, so I only worry about what is the energies associated with the electromagnetic wave. I don't need anything more than that. I'm not bothering about what is the electric field or what is a magnetic field. I would see overall what is the strength of electric field and magnetic field together would create the energy in the system. That is what I am only knowing. I am bothered. So that is here is purely quantum. Even though I started with the classical physics, classical electrodynamics, I went on to describe pure quantum. Okay, so that is the answer for that Maxwell's question. Can we transmit quantum wave if we can go through few challenges on it. I am not getting what is the question. Can we transmit quantum wave? If so, can you throw few challenges on it? I'm not getting. I think you mean to say quantum wave going through some medium. And maybe you can reframe the question. Yeah, it's I know it's very informative, but I need some involvement from you people just to go through it. Then only you would appreciate. Okay, right? Yeah, can we transmit quantum wave via antenna? If so, can you go through few challenges on it? Okay, now I get it. What is your question? You are saying through antenna, we usually send continuous waveforms. So can we send in the form of discrete energy states? Okay. Yeah, basically it is like some digital communication or something. So I'm not an experimentalist. So I have very less background in that. So I would say possibly yes. Okay, it's possible. Okay. Do we study quantum sensors, advantages over classical sensors? No. So the topics which were given to me to study, like teach the basics of sensors, basics of photons, single and entangled, and then go on to study few particular sensors like gravimetry, atomic clock, and magnetometry. Okay, so these three things definitely we'll discuss, and the state of the art in quantum sensing. Okay, so how quantum sensing is better compared to classical sensing. So the state of art, the mechanism that we will study. So you, in a way, we would say how quantum sensing is advantages over classical sensing would be discussed. Yes, yeah, but not as such one-to-one. We will not compare, but we will see some scenarios where quantum sensing can outplay the classical sensing. Yeah. Okay, so any questions further? No. Right. Fine. Looking at my hand note, I would say there is not much. Okay, anyway, I'll send it and share the both of them. Okay. Okay, so in the tomorrow's session, we will go through a discussion on the Fock states and the Poisson statistics, and there is something called coherent states and photon statistics and Poisson statistics for coherent states. We'll discuss. Okay, and something more that I will prepare and add it to this. Okay. Yeah, I will conclude here. If you happen to have any doubts, please do get in touch. And the quantum sensing and quantum entanglement sensing is different. We'll touch that definitely. So quantum sensing could be possible with a single atom or a single qubit. When I say quantum sensing with entangled setup, means there must be two or more than two are involved. Okay. So interestingly, the moment I use multiple qubits, not just multiple qubits, they're entangled in the first place. In that case, I can improve the accuracy of the sensing. Okay, so the sense entanglement is going to add the extra benefit or advantages to the sensors. That exactly we are going to touch also in the sessions. Okay.
Thank you, Ashwath sir. Thank you for today's session. And Ashwath sir, mail ID is also there. You can drop a mail in case there is something urgent. Tomorrow also, while sir starts, you can put in the chat, and whenever sir is giving a break, he will address those queries. Many are requesting that session should start by 4 o'clock, sir. Some of them are traveling at 4 actually. Some of their college closes at 4. So yeah, please don't worry, because to conclude it's very difficult. So what you can try to do is try to get into the bus and watch the remaining part of in the video. We are sharing immediately within half an hour to 1 hour. We are sharing. So while you reach home, you can open the video and listen to the last part. I think it will benefit, because to conclude, it will be good that that day's content is covered, right? So we request, thank you, sir, for your time. And tomorrow, 2 o'clock, we'll meet, and a few more days left. I hope you are all preparing for the exam also. Nivedita ma'am has sent her questions. Ashwath sir will be sending our questions. So on Friday, we'll be opening the quiz for you. If you want, we will open it on Saturday. That's also fine. Accordingly, you can suggest, you can give feedback. We will open it for 2 days. Maybe if it's there, then Saturday, and if you open on Saturday, then we'll give you time till Monday evening or Monday midnight, right? So we will close it, and then based on that, this time we will not request you to write the quiz. Those who don't write the quiz, it will miss. Thank you, sir, for giving the written notes. This is a very unique way of, very easy to understand. And also the handwritten notes that you are following in the lecture also, that is being shared. So, and then a very new topic, many have not touched upon sensing. So thank you so much. Thank you, Dr. Ashwath. So we'll break here. Tomorrow we will meet at 2 o'clock. Dr. Ashwath has shared his number. So in case you want to note it, don't call, please put WhatsApp messages. It is better. If you keep calling, then there'll be many calls. But those who are interested, you can drop a message. Sir will respond at his leisure, right? So thank you so much, all of you. We'll meet tomorrow.
Yeah, I promise tomorrow we'll